All right, well, now that we've had a chance to talk about derivatives extensively and also have some exposure to higher order derivatives, let's start looking at some of the uses or applications of derivatives. And so this section is all about finding and working with problems involving position, velocity, and acceleration. In mathematics and oftentimes in physics, you'll see that a function that describes the position of an object that is in motion um, this is often described using what's called S of t. So I'll write this right next to it. So S of t. So when you see that notation, that's often describing the position or the location of an object at a given time. Well, then finding the derivative of this position function allows us to then look at that object's velocity, right? So the rate at which that position is changing. So S of t describes the position of an object at a given time. Velocity describes the rate of change in that position. Well, what about when we take the derivative of a velocity function, or what we know as the second derivative of the position function? Well, that then gives us what's called our acceleration. So the rate at which that rate of change, or the velocity, is changing. So the rate of change of velocity, if you will. So a couple of quick notes, things that we want to keep in mind as before we work in through some of these problems. So first off, so if we know that position is denoted using the S of t function, when we're describing initial position, that is the position of the object at t is equal to 0, when the time is equal to 0. So one way of describing that is to say S of 0. It's our position function evaluated at 0. What about our initial velocity then? Well, our initial velocity is again at t is equal to 0 because it's the velocity when we're first starting off. So sometimes you might see v of 0 like this, or sometimes you might even see this, but v of 0 is often what's commonly used. Now, in everyday language, the terms velocity and speed are often used interchangeably, but they're actually different. Speed is simply velocity irrespective of sign. Well, what do I mean by that? Well, when we're tracking the movement of an object on a coordinate plane or on a number line, we see that velocity has a sign element. So let me highlight that. Velocity has a sign element. So in other words, velocity is the speed with direction. We see that when the velocity is positive, so when the velocity is positive, we move to the right on the number line. When our velocity is negative, we move to the left on our number line. Speed is simply the absolute value of velocity, the absolute value of velocity, right? So it's looking at the rate of change of the position irrespective of sign. It doesn't matter if it's moving to the right or to the left, it's just simply tracking that rate of change. Now, on that note, let's use that to think a little bit about displacement versus total distance. So displacement is the net change in position, net change in position. And I'll do an example real quick just to make sure I highlight the difference between the two. So we will find the displacement by taking the final position minus the initial position, or wherever we're comparing it to. Total distance, on the other hand, is the total distance traveled in the interval. Total distance traveled in the interval. So what it does, it takes into account all direction changes. So takes into account all direction changes, all direction changes. So just real quick, there's a very basic example. Suppose an object had a positive velocity, so it moved to the right, let's just say 3 units. And then after a given amount of time, it then moved back 4 units. We would see here that the displacement of this object is -1. 3 minus 4 is -1, right? However, what is the total distance traveled here? The total distance traveled here would be 7, because you can think of it as 3 steps forward, 7 steps back. You've taken a total of 7 steps. But right now, compared to where you were initially, you really only have moved -1 steps back, or 1 step back, if you will. So that's one way of thinking about displacement versus total distance. And I think it'll be most helpful if we start looking at a couple different problems here, just to kind of think a little bit about these problems, or these concepts, I should say. So let's look at a few of these examples. So let's start working through them. So suppose you had a position function, s of t here is tq plus t. Let's find the velocity function and the acceleration function. So we've got here v of t. Let me actually change colors. V of t is simply going to be the derivative of our position function, which in this case, using the power rule, is just 3t squared plus 1. Now, what is the acceleration function? The acceleration function is the derivative of our velocity function. So I'm now going to take the derivative of our velocity function, which again, using the power rule, is just simply 6t. Now, what about this part here? Let me change this. When is the object at rest? Well, an object is at rest when the velocity is equal to 0. When our velocity function is equal to 0. When it's not moving, that's when it's at rest. So what we want to do is we want to set v of t equal to 0. So I'm going to write 0 is equal to 3t squared plus 1. And when we solve this algebraically, we can see that t squared is equal to negative 1/3. And think about what happens if I try to take the square root of both sides, or to extract roots here. Well, taking the square root of negative 1/3, well, that's not going to result in a real number. So what does that mean for us? We can say that the object, therefore, here in this particular function, is never at rest. There's never a time where this object is not moving. There's always going to be a velocity. All right, let's try another example. So in this problem here, in this next set of problems, we're going to use s of t here, which is this particular function. All right, so that's the function that we're going to use for a number of these problems below. So we've got an object that is moving in a horizontal line, and let's just start running through a few of these. So if s of t is equal to that, what is the initial position of the object? Well, the initial position, again, is when t is equal to 0. So let's evaluate the position function at 0. Let's actually do this. At 0. So s of 0 is going to be, if I evaluate this function here that's highlighted at 0, so 16 times 0 is 0, minus 36 times 0 is 0, plus 24. So s of 0 is equal to 24. And again, 24 what? We want to make sure that we're writing units, which are incredibly important when we're dealing with things like velocity, acceleration, and location or position of an object. So we want to say 24. I believe it was given to us in feet for distance, and keep in mind we're going to be using seconds for time. So this is going to be 24 feet. Okay. All right. Let's look at the next problem. What is the velocity of the object at t equals 1 second? Well, that's just simply going to be my velocity function evaluated at 1. So that's going to be, well, you know what? Actually, before I even do this, I'm going to need my velocity function. So we know, again, v of t is equal to the derivative of s, which in this case, using the power rule, we're going to go 3 times 16. So that's 48, decrement that power, t squared. And then 2 times 36 is going to give me negative 72t, and the derivative of 24, that constant is just 0. So now I'm ready to evaluate this derivative at 1. So 48 times 1 is just 48, minus 72 times 1, which is just negative, it's just 72. So now we're going to say negative 24. And what's our unit here? We're changing feet per second. So it's negative 24 feet per second. Now take a look at number 4. Number 4 is asking us for the speed of the object at t equals 1 second. Well, again, what is speed? Speed is simply the absolute value of velocity. So what did we say our velocity was? Negative 24. So the speed, the rate of change here, is 24 feet per second. Again, we're not looking at whether or not we're moving to the right or to the left. We don't care about direction when we're discussing speed. It's just simply the rate of change. Moving on, let's try number 5 now. Number 5 is asking, what is the acceleration of the object at t equals 1? Well, again, acceleration is the derivative of, not s of t, the derivative of our velocity function, which in this case, if what do we say our derivative velocity function was? 48t squared minus 72t. So we're going to say 96t minus 72. And we're going to evaluate this acceleration function at 1. So we've got 96 minus 72, and that's going to give us just 24 feet per second squared because we're discussing acceleration. Now, moving on to number 6. At what time is the object at rest? Well, ask yourself, when would an object be at rest? An object is at rest when the velocity is equal to 0. So we're going to take our velocity function and we're going to set it equal to 0. So we have 48t squared minus 72t. And we're going to just solve this as a quadratic, which we can factor out our common factors of 24t. This would be 2t minus 3, which then gives me the following zeros. We got 0 and positive 3 halves. And the unit would be seconds. Okay, so that's when the object is at rest. All right, let's try number 7 now. Over what time intervals is the object moving right? And when would it be moving to the left? Well, we're going to look at our velocity function here, but most importantly, we're going to be looking at its signs. Now, you can draw a number line here, and I'm going to actually mark 0 as one endpoint here. And the reason for that is I'm not concerned about negative time. So I want to look at 0 and onward. And using our previous problem, we know that we have 0 and 3 halves as the zeros to our velocity function. That is to say, that is when the function is equal to 0, and that is when there are going to be possible sign changes. So we're going to mark 0 and 3 halves on our number line, and we're going to try to test values between 0 and 3 halves, and then 3 halves from and on. So what would be an easy number to try plugging in between 0 and 3 halves? Well, let's just try something like 1. What would v of 1 be? Well, we already found that earlier. We know that v of 1 is equal to negative 24 feet per second, which we saw here. So we know that our velocity is negative. Let me just do this in red. It's negative between 0 and 3 half seconds. Well, what about something beyond that? So let's just say something, for example, like what would v of 2 be? Let's do that. V of 2. Well, if I plug 2 into our function, we would have just go ahead and try testing something like that in there, and we should see that that should be greater than 0. Right? If I'm not mistaken. Yeah, we're going to get a positive value. So we're seeing that our function is moving to the left when t is between 0 and 3 half seconds. And it's going to move to the right when t is greater than 1.5 seconds. So we can determine the direction by just looking at the sign of the velocity. Remember, positive, we're moving to the right. Negative, we're moving to the left. Well, now let's find the total distance. Well, let's think about this for a second. First off, we want to start with our initial position. So what was the initial position of our function? If we plug 0 into our function, I believe we said we got 24 feet. So if you think of a number line, we can say that we started out at a location of 24 feet from 0, okay? Now, where would be the next place where our velocity would change? Well, we said again in our previous problem, the next place would be at 3 half seconds. And we care about this because if we're finding total distance, we want to know where are we going to the right and where are we going to the left. At 3 half seconds, when we plug that into our position function, and let's just plug that in, just take a moment, do that. I'm not going to work it out on paper, but if you have your calculator on, you can check that. But I believe when we plug in 3 halves, we should get negative 3. Okay? Now, I'm going to just make a quick note here. It's important to note that how many units have you traveled so far? Well, you've traveled a total of 27 units to the left because you started out at 24 and then you made your way all the way to negative 3. So you've traveled a total of 27 units. Now, where would be the next place we'd want to check? Well, the problem's asking between 0 and 2. So it makes sense that we have to evaluate our position function at 2. So at s of 2, we have 8. By the way, these are all feet. Okay, so now we're at 8. So now ask yourself, if you were at -3 on the number line, and I can maybe even just draw this, -3, and now you're at 8, what's this total distance that you traveled now from 3/2 seconds to 2 seconds? Well, this is a total of 11 steps to the right. So think about this for a second. We went, and I can even just continue drawing all this. So this is obviously not to scale, but if I write 24 here, you went initially from 24 to -3, you went 27 units to the left, and then from -3 to +8, you went 11 steps to the right. So what is the total distance? We would want to add these two values together, and you should see that we get a total of 38 feet. And a little later on in the course, we're going to find ways to use some other calculus to find these, but right now we're comfortable just adding up positive and negative values. All right, so now let's move on to number 9. When is the velocity of the object equal to 54 feet per second? Again, that means now we need to find when our velocity function is equal to 54. Well, again, our velocity function is 48t squared minus 72t. Set that equal to 54, which we're going to solve this like a quadratic. And I don't believe this is actually factorable. So we're going to use our calculator for this, and I can't pull that up right now, but if you go ahead and put this into your graphing calculator or just your equation solver on your calculator, you should end up with t is approximately equal to -0.549 and 2.049 seconds. Now, think about these values in the context of the problem. Does it make sense for us to be using a negative time value? And the answer is no. So the only valid t value that we would be looking at would be 2.049 seconds. That's the exact time, or I should say approximate time, that the velocity is equal to 54 feet per second. Now finally, what is the displacement of the object between t is equal to 0 and t is equal to 2 seconds? Well, this displacement, again, is not the total distance traveled, but just really looking at the final position minus the initial position. So we can say that at s of 2, that was 8. S of 0 is 24. So at 2, when you were after 2 seconds, you were at the position of being 8 feet from 0. And when you first started, you were 24 feet from 0. So you've moved back 16 feet from where you first started. Okay, so again, when you first started, you were at 24. When after two seconds, you were at 8. So you've moved back 16 feet. That's what displacement is measuring there. Okay, and let's do one more exercise to really make sure that we're comfortable with things like velocity. Now this time looking at a graph. So take a moment and pause the video and work through some of these questions, and we'll discuss in just a second. All right, so we have a graph that shows the position of a race car or an RC car. So was a car going faster at point A or point B? Well, we want to be looking at the velocity to determine whether or not it's going faster. And again, velocity is simply the derivative of our position function. And what did we say early on that a derivative was? It represents the slope of the tangent line. So if that's the case, then we can kind of just compare the slopes of the tangent lines here. And that's actually, I don't want to put an arrow there, but we're kind of just comparing these tangent lines here. I actually probably should put it on the other side. Okay. Actually, it's really hard to kind of tell whether or not it's still concave up or concave down there, but you get the idea. We see that the slope of the tangent line seems to be steeper at B. Okay. Now, between which 2 points is the car stopped? Well, we would say between C and D, and ask yourself why. Well, that's when our velocity appears to be equal to 0, because we seem to have a horizontal tangent line there, right? Again, the slope of the tangent line between C and D appears to be 0. At which point was the car's velocity the greatest? Well, looks like then we would want to say that we have the steepest positive tangent line at B. The steepest positive tangent line at B. Now, why is that important? Because the next question is saying, at which point was the car's speed the greatest? Well, now we're looking at speed, which doesn't care about whether or not your tangent line slope is positive or negative. Well, clearly the steepest part of our graph appears to be right around here at point E. Okay, so we would say E here because the absolute value function of our velocity appears to be the greatest there. Now, before I end this lesson, I just wanted to briefly discuss vertical motion, and we're still doing a lot of the same things here, but just some things to keep in mind. To find when an object is on the ground, we would say when our position function is equal to 0. So now we're looking at objects that move up and down vertically. To find when an object is at its maximum height, we would then want to just look at when v of t is equal to 0, because after that, the velocity could change signs from positive to negative, whether or not it's moving up or moving down. So if an object moves up, then once it reaches its peak, that's when the velocity is going to be equal to v of t is equal to 0. And then after that, the object would then move down. And that's when we would have the negative velocity there. So let's find the initial velocity for this particular position function here. So we've got s of t, which describes the position for a ball that is thrown into the air from the top of a building. So what is the initial velocity? Well, here, if we know that our velocity function is the derivative of our position function, so we're going to say negative 32t plus 48. The initial velocity is when t is equal to 0, so plug in 0 for t, and we get 48 feet per second. Now, at what time does the ball hit the ground? Well, the ball is going to hit the ground when our position is equal to 0, when s of t is equal to 0. So I'm going to solve this. And I think I can divide everything here by 16, in which case I would have t squared, or negative 16 actually, because I want that positive leading coefficient. So I'm going to rewrite this as that. And I think this is pretty easily factorable. We got t minus 5, t plus 2, in which case t is equal to 5 and negative 2. And as we saw in the previous problem, I'm not really concerned with negative time values. So I would just say when t is equal to 5 seconds. Okay. Finally, at what time does the ball reach its maximum height? We said earlier that's when v of t is equal to 0. So I'm going to set my velocity function equal to 0. And this should be a pretty straightforward one to solve. We can maybe even just do this. So t then would just be 48 over 32 simplifies to 3/2 seconds. So that's when the ball reaches its maximum height. So hopefully this was helpful in seeing some applications of working with derivatives and higher order derivatives of things like position functions.